Hello everyone. Welcome to the Tektronix webinar on Measurement Options DisplayPort 1.4. My name is Emsia. Today I'm going to show you measurement options to speed up your DisplayPort test and to do it in an efficient way. At the end of the webinar, I'll do for you a demonstration which shows the different options for you to understand how to do it using Tektronix software. So let's get started.
Hello everyone, welcome to my presentation on DisplayPort measurement options. My name is Emsia. We are going to talk about DisplayPort compliance test system in an efficient way to speed up the required measurements and save time. We present the functionality of our unique software with two different setups. Each setup enables the user to optimize the time and measurement combinations which are defined in DisplayPort compliance test system setup. A brief introduction about me. I'm Ali Emsia, optical application engineer. I'm with Tektronix since January 2019. My expertise are optical communications, coherent optics, and photonics. I did my PhD in Technical University of Darmstadt, Germany. For more than 2 years, I worked in cable operator industry and developed a new optical return path receiver for fiber to the home architecture. This receiver is going to be used in data centers in DOCSIS 3 technology. My specialty is to serve the customer in a best way which fits their application. The presentation is outlined as follows. Today we will be covering the DisplayPort compliance test measurement options. First off, we are going to briefly talk about the DP standard. We'll see what the latest demand for the DisplayPort is. After that, we move to the challenges which may face during your DP-CTS measurement. We will be showing the advantages of our test solution and explain why time efficiency in your test matters. Then we discuss about the Tektronix measurement options for DP compliance test system. We compare three different setups. First one is taken as the reference setup. We explain the difference between each techniques. We'll introduce the RF switch matrix that enables the user to automate the DisplayPort measurement and allows the user to reduce the test time. After that, we'll present a unique Tektronix tri-mode probe P7720 and show its benefits. We will finalize the presentation by showing the cost and time efficiency of the Tektronix equipment. Finally, the presentation will be able to show the attendees which technique they need according to their budget. Here you see the DisplayPort standard. On the left side, as you can see, we have a summary of different standards from DP 1.1 to DP 2.0. As the bandwidth demand grows continuously, the VESA community introduced the upgrade DP 2.0 version. The bitrate goes to 77.4 gigabits per second. It enables 8K beyond resolution. It has improved the augmented reality and virtual reality in 4K resolution. The available link rate has been increased up to 20 gigabits per second per lane with 128-bit, 132-bit channel coding. That translates into a maximum of 77 gigabits per second with support for 8K video. DP02 is backward compatible with previous versions of DisplayPort, and it is projected to appear on the market by late 2020. On the right side, you see the table of standards summaries with their corresponding bit rates, as well as target monitor resolutions. Here our focus will be DP 1.4 with a bit rate of 8.1 gigabits per second. Here we see a general schematic of a DisplayPort. It consists of 4 main differential lanes. The clock is embedded in the data lanes. Clock is 1/10 of the bit rate. The differential auxiliary channel is used for line management and device control between source and sink. It is a bidirectional transmission. And the hot plug detects interrupt requests the connection as soon as the cable is connected. Here we see the compliance test points as standard as defined. So TP1 is the pin at a transmitter device. TP2 is at the test interface on a test access fixture near the end. We have the TP3 at the test interface on a text access fixture far end. So the cable is between TP2 and TP3. They have the TP3 equalizer, which the equalizer is applied in the DSP to emulate the channel. We have TP4 at the pins of a receiving device at the receiver side. We have 2 different test points, normative and informative. So typically we acquire the signals at TP2 and apply cable emulator filter dealing analysis to arrive at a test point which is called TP3 equalizer. According to the DP specifications, we should test the signals assuming it's passed through a burst cable or when there is no or zero cable. Finally, we have a test point TP4 at the pins of receiver chips and is an informative test point as far as transmitter testing is concerned. Informative is a designation of a test that is not required for compliance but is considered important from a characterization standpoint. It is provided for informational purposes only. Normative is a designation of a test that is required for compliance test. So here we'll be doing the TP3 equalizer. So let's see how many tests do we need to perform. In this slide we show a summary of the test for DP 1.4 CTS. The tests consist of 5 categories: standard, skew, level verification, auxiliary, and spread spectrum clock tests. They are mainly normative tests. All these tests must be combined to be able to perform a compliance test. Let's see the number of waveforms need to be acquired to do this test. We focus on a standard test for the sake of brevity. So let's go a bit into a detail of these tests. We have a standard test which tests for eye diagram, jitter, random jitter, deterministic jitter, and total jitter, and frequency and noise. We have a skew tests at high operating speeds. It is important to understand the skew between legs of each lane and between 2 lanes. For this, DisplayPort defines intra and inter-pair skew tests to ensure the source design meets the specification so that the receiver can receive and output the data within the allowable range of these skew requirements. Another test is level verification. 2 tests are defined under this category: pre-emphasis and non-pre-emphasis level verification tests. The CTS defines the table that describes the relation between the pre-emphasis level and voltage swing settings. Some of the settings need to be tested mandatorily, while others are optional. So these tests ensure that the source device meets these table criteria before passing compliance. Auxiliary test is the next test. There are three tests defined on the auxiliary test: auxiliary I, sensitivity, and in-rush current tests. It ensures the auxiliary communication takes place successfully between source and sink devices. Another test is the spread spectrum clock. There are three tests defined here as well: SSC frequency modulation, deviation, and variation. It's optional for a source device to support SSC. But if the device supports SSC, then it is recommended to test for transmitter compliance with SSE turned on. We'll be focusing on standard tests, especially eye diagram testing. Let's see how many measurements do we have to do. So in order to be able to do the measurements, we need some tools or software to emulate the DisplayPort measurement. According to DP 1.4 CTS, the eye diagram test must pass the TP3 EQ test point, as mentioned in the previous slide. These uses both worst case and zero length cable model. It is required that source provides at least one unique setting: voltage swing, pre-emphasis level, post cursor 2 level, and equalization that will pass each cable model. Here you'll see several blocks which perform unique operation in the test. First, we capture the pattern as a waveform at the compliance settings. Then we apply HBR3 worst case cable model, simulating the worst scenario. Then we apply the CTLE settings and optimize the CTLE based on the maximum eye opening, which can be determined by measuring eye area or height. Now, if you already know what is the optimum CTLE setting for your device, then you can directly choose that particular CTLE setting. Once you have the optimum CTLE setting determined, you apply the one-tap decision feedback equalizer as defined in the specifications and generate the final eye diagram as shown here. There is a provision added in the text compliance test tool shown in the screenshot to perform the measurement easily. The optimized CTLE value is also used to create a new waveform for performing the total jitter. The total jitter measurement result is based on eye diagram pass condition, so testing gets challenging as we have one test dependent on the other. The adaptive mask generation defined for HBR2 and HBR3 continue to hold good in DP 1.4, so generated mask can be either symmetric or kite shape as shown in the eye diagram image. On this slide, we'll see the eye diagram tests. Eye diagram tests includes 4 data rates. HBR3, we have 4 distinguished voltage swings for each data rate. So we have 400 millivolt differential voltage swing, and we need 4 different pre-emphasis levels: 0 dB, 3.5 dB, 6 dB, and 9.5 dB. Similarly, for the next voltage swing, we do 3 pre-emphasis levels. As we go further, we reduce the number of pre-emphasis level and we increase the voltage swing to do our compliance test. For the next bit rate, we have the same number of tests, which is HBR2. We have the same voltage swings and we have similarly under each voltage swing the same pre-emphasis levels. For the next 2 lower data rates, we only use 1 voltage swing level and 1 pre-emphasis level. So we have high bit rate and reduced bit rate, each with 800 millivolts voltage swing, and the pre-emphasis is set to 0 dB. As you can see here, for each lane you need 20 waveforms, which means acquiring 20 waveforms, and the standard recommends to turn on the SSC, spread spectrum clock, if your dot supports it. So we have 10 waveforms multiplied by 2 gives you 20 waveforms per lane. And if you multiply it by 4, you get your 4 bit rates. And we are talking about one lane. We have 4 lanes as explained before. So in total, for eye diagram test, we need 168 waveforms. So let's see how many acquisitions do we need for pre-emphasis level. This test evaluates the effect of pre-emphasis of the source waveform by measuring the peak differential amplitude to assure accuracy of the pre-emphasis setting. As before, we need to test different combinations. We have 4 different data rates. Under HBR3, we have 4 different voltage swings. We set the pre-emphasis level first to 0 dB. We do the tests, and we do the differential pre-emphasis levels as shown here. So for example, in case of 400 millivolt, we do a differential level 3.5 and 0 dB. Similarly, we do between 6 dB and 3.5 dB and 9.5 and 6 dB. And as we go further, we set the pre-emphasis level accordingly. This is the same for the next 3 data rates. So when we count all the acquisitions, we have to do 320 waveforms for this test. Now we go to another test, which is called non-pre-emphasis test. The test ensures that the system budget is obeyed and ensures that the level settings are monotonic so that the sink can rely on the source to incrementally increase upon the request by sink, as defined in the standard. So the source is given a range of expected output for each level setting that correlates with the system budget elements, such as the cable loss and the receiver eye minimum and maximum values and PC board transmission line loss. Further, the link must benefit from increasing level settings. The pre-emphasis level is set to 0 dB, and the peak-to-peak voltage swing is calculated between 2 different levels. As you can see on the tree, what just explained is clear now. So the pre-emphasis level is set to 0 dB for all data rates, and there will be a differential peak-to-peak voltage swing calculation between different levels. So we have, for example, 600 millivolt to 400, 800 to 600, and 1200 millivolt to 800. This is the same for all data rates. So for this test, in total, we need to acquire 96 waveforms. Let's see a summary of the measurements. On the left side in the table, you see the parameters and the combinations. We have 4 data rates as mentioned, different patterns defined by a standard, pre-emphasis levels, 4 levels. We have 4 levels of voltage swing and 1, 2, 4 lanes. And we have a spread spectrum clock turned on or off. And we outlined here the number of waveforms, eye diagram 168 waveforms, pre-emphasis 320 waveforms, and non-pre-emphasis 96. For the sake of brevity, we didn't show the tree of total jitter. So it's similar to the eye diagram, which is 168. As you can see, 752 acquisitions are required to do the DP 1.4 normative tests, beside all other tests which mentioned earlier in the slides. Tektronix successfully showed a HBR2 test times of approximately 6 hours, which is a really breakthrough compared to a real-world benchmarking HBR2 test time of more than 11 hours. This is very time consuming measurement. The time matters when you do a DP-CTS test. If you had no automated measurement process, you cannot measure such a time consuming measurement. So we will show you a time efficiency and how to speed up your measurements and how you increase your quality of your CTS measurement. Let's look into the challenges we have while measuring the DP 1.4 CTS. Assume that you have a dot to be tested. You need a DisplayPort fixture that is defined by a standard. You connect the fixture to the sink and the lanes from the other side to the scope. Here you see an example of non-automated test. Assuming that you have the DP 1.4 CTS software, you have to keep swapping the lanes to run some of the previously mentioned tests. To do so, you must unscrew and screw the cables. Here we show 4 lanes already screwed. That's why you see the number of screw 4. We roughly estimated the time for unscrewing the cables from 5 to 10 seconds. That's an estimation. So the total time here is 20 to 40 seconds for 4 lanes. As we move forward, we add up the number of screwing, unscrewing, and the time consumption for this process. So you see here now we have the lane 0, which is the clock lane, and we have the lane 2. So we had to unscrew lane 1, 2 cables, so the number of unscrews are 2 now, and screw 2 cables, which is lane 2, differential lane 2. So in total we have screwed 6 times, and then now the time consumption is incremented to 40 to 60 seconds. We move forward to the next differential lane, which is the lane 3. So the number of screwing, unscrewing is increasing. So do the time consumption. Remember, we have 4 lanes. Now we are doing the lanes comparison. Now we connect the lane 1 one leg and lane 2 another leg to the scope, and we keep the clock on channel 1 and 2 of the scopes. So as you see, doing this process, it consumes lots of time, and you waste time by screwing and unscrewing. The connector life is also going down. Similarly, we do the same test for lane 1 and lane 3. We keep disconnecting and connecting the legs on the scope, which is not efficient at all, and we are exceeding the time which we planned for our project, right? Again comes the next line, and we keep unscrewing, screwing, wasting time, wasting our connector. This ends up to measurement errors. The repeatability will be reduced. The connector life, SMA connectors are fragile. The more you torque, the less will be their life. And the most important thing, time is money, right? So let's remind ourselves, using this process will reduce the repeatability of your measurement. Since you open and close the connection many times, you cannot get the similar results the next time when you do the same measurement. We need 752 waveforms for 4 lanes. Using this process will waste your time. How many seconds you just need to unscrew and screw the legs and to reduce the lifetime of your connector. Will you do that? So, as mentioned, we have seen that this is not a nice measurement technique to go for. That's why we introduce here the Tektronix software, which enables the user to do all these measurements automatically. Now let's see Tektronix DisplayPort CTS software. We show the functionality of the software, and this software enables the user to save time and cost to run his test. Here you see the graphical user interface of DisplayPort Text Express software. So on the dot menu, you have your dot ID, you name your measurement, which measurement are you going to do. You can have live waveform mode, which you acquire the signal live and you do the processing, or you can have a previously recorded waveform file, and on the base of this waveform you can do your processing. View mode shows the compliance test as well as the advanced mode. In the compliance test you cannot change the parameters, but in the advanced mode you are free to change the parameters as you like. Device will be the DisplayPort, version is the different versions of the standard, and we have connector type, standard and type C connector. Under the device profile, you can select between different combinations, different data rates. We have voltage swing from level 0 to level 3. We have pre-emphasis level 0, 1, and 2. SSC both, which means turn off and turn on. Turn off the SSC and do the measurements, and turn on the SSC and do the measurements. There is a test mode, which is for automation or manual mode, or DPR 100, which is beyond the focus of this presentation. And you can just prompt the signal validation if it fails, or you can pass it manually if your pattern is different or if your bit rate is different. You can pass it even if they don't comply with the compliance tests as you like. So you have a freedom to do your own measurement. Most importantly is this part, which you can select your probes or multi-lane RF switch. So you have your switch matrix. This is when you click on the switch matrix. As you see, you have your menu, which you can select between different switches, and you can automate your measurement without any personal intervention. That's an advantage. You can de-embed your lanes here, your switch, your path, to reduce the effect of the channel loss. You can connect it through the LAN or GPIB. This operates with the Tech Express and DPO-JET. You can save, recall switch configurations depending on your configuration, setup configuration. There is a built-in error handling to support easy and error-free configuration. And at the end you can save your results here. You have the graphical view, which shows on which port you connect your cable. Here you see the Tektronix Ketley RF switch with different switch relays, 1 to 2 or 1 to 6. And this is a graphical view how to use the relays. There is an example on the left side. So we have a fixture, we have a data under the test, and as you can see we have 4 lanes. The differential lanes are connected to different ports of the RF switch. We have 4 relays in the example, and the midpoint is connected to the scope channel, channel 1 through channel 4. So without intervention of the user, you can automate your measurement to switch between the lanes, and you avoid swapping and unscrewing the lanes, which saves your time, saves your money, and saves your connector. Here is another menu of the DisplayPort Text Express software. You have the text selection. Under the text selection, you can select different measurements you wish according to the standards, and you can configure your parameters under the configure. If you go to the advanced mode, you can change your clock type, clock recovery type, you can change your bandwidth, everything, which allows you to go beyond what a standard defines. This is the acquisition menu, shows lively at which acquisition you are, what's going on, which pattern is on the lanes, and so forth. And we have the preferences, very important menu. Here you can increase your number of acquisitions to see the repeatability of your experiment and to control the repeatability, test it if your experiment is repeatable. Another menu, we have the status, test status. So here it shows at which state it is during the measurement, and on the right side the software allows you to save the whole measured parameters, waveforms, and the results in different formats. It's really a user-friendly software and time-efficient software from the Tektronix. With the introduction of DFE and CTLE optimization in DP 1.4 that we discussed earlier, it becomes very important to study the overall channel behavior. There is a need to simulate the worst channel and understand the effects it has on the transmitted signal. Many times there are problems probing a specific location in the signal path. There may be components in the path which may be contributing to failures leading to closed eye. This is when a channel analysis tool like STLA comes into the picture. STLA stands for Serial Data Link Analysis. This tool helps virtual probing through different test points and helps open a closed eye by removing effects of the cables, probes, or fixtures. What's more, you can use to embed 8 different components in the signal path, or de-embed up to 8 different components. So the upper part you see is the measurement circuit, and lower part is the simulation circuit. On the upper part, you de-embed these parameters or the filters, the effects which you already measured, and in the lower you simulate your specific channel or your required channel and you see the effect. This tool can model the blocks by accepting the industry standard S-parameter files. The tool also helps user to create their own S-parameter file, which can then be converted to filter file later. The tool has a capability to accept input waveform, perform channel analysis, and output final waveform onto the scope math reference channels, where DPOJet can be used to run measurements directly on the generated waveforms and other software. We have recently added a standard module for DisplayPort 1.4 under STLA tool. By selecting this standard and the required CTLE DFE settings, user can generate their own optimized eye diagrams and study the dot behavior. The Tech Express automation tool interacts with STLA during automated compliance testing to find the optimized CTLE setting, as you can see on the right side. One of the most powerful and general-purpose signal analysis debugging tools in the industry is the DPOJet tool. This tool has literally hundreds of measurements which should help you to debug and determine the root cause of the failure in your system easily. You can add up to 99 different measurements in a single run and compare the results. You can vary one parameter at a time between measurements or add same measurement on different channels and study which of the channel has an issue. there is a comprehensive measurement library built for jitter, noise, eye, amplitude, and timing analysis. While that's more of a basic analysis support, we do have a DP-specific DPUJet plugin available. Just add the failed DP measurement on the DPUJet, acquire the desired signal, and perform through analysis. There are different plots available too, like the bathtub histogram eye diagram, which gives a pictorial representation of the system behavior, and DPUJet lets to save these results into a report as well. This model of coupling measurements into DPUJet library takes user much closer to the measurement than having them coupled tightly to the automation tool. We have seen users who have written their own DPUJet set of files around these measurements and automated them as a part of their test system. So you see the amount of flexibility DPUJet offers when it comes to the debugging measurement failures. Now let's focus on the setup. We have used reference setup. Before going that, so up to now, we introduced the Text Express DisplayPort, SDLA, and DPUJet, the most powerful softwares and necessary to run a compliance test system in an efficient way. Here is our reference setup for our proof of concept. As you can see, we have a source AWG70K type B or series B from Tektronix. We have two phase matched cables with the corresponding S parameters, which will be used in the SDLA to embed the cables inside the software. We have our real-time scope DPO 73304SX 33 GHz series, and the measurement parameters which used for this reference setup was DP 1.4 HBR3 8.1 gigabits per second, voltage swing 800 millivolt, pre-emphasis 0 dBm, and for the sake of brevity we only tested eye diagram test here for one data rate. Here are the results. So we tested two eye diagrams for two different cases. So we tested it on the scope in the software, and TP3 EQ was the test point that we used. So we used two CTLE levels, 0 dB and -5 dB. 0 dB was for the zero length case as a cable, and worst case -5 dB was for the cable which leads to the -5 dB attenuation. As you can see on the left side, we have an open clean eye diagram with 856 millivolt eye amplitude, eye height, and on the right side we have the 326 eye height. So we took these two values as the reference values for our evaluation using the RF switch matrix and Tektronix probe, which will be mentioned shortly. And these two tests just passed the compliance test of HBR3. Here is the next setup. We put the RF switch matrix in the experiment. We used two pair of cables, which means 4 phase matched cables. The Tektronix Keithley switch model was S46T, and we used the same parameters and the levels for the testing in order to be able to compare our results with the reference results and see the signal degradation when we put the RF switch in the experiment. And it must be mentioned that the S parameters were calculated using TDR test and measurement equipment from the Tektronix. So we are emulating two separate channels. To do that, we have lane positive and connected to relay A, and lane 0 negative is connected to relay B, and on the scope we connect this to channel 3, and for the other lane we connect it to channel 1. Now let's see the results here. We have also the embedded, the cables effects and the switch matrix loss effects here under the embed menu. Now you see the results here on top, two eye diagrams. On top left we have 0 length CTLE 0 dB, which the eye is completely clean and open, and eye height is 730 millivolt. And on the right side the worst case is simulated with -8 dB, and in all measurements we didn't turn on the SSC. We just wanted to show the concept and the advantage of RF switch matrix solution and probe solution. So in the worst case we have 226 millivolts. When we de-embed the cable and RF switch, we see the effect. So we have a bit of the embedding effect and amplification, and there is a bit of difference between the eye height around 20 millivolts on the right side on the worst case, and on the left side we have around 15 millivolts approximately. So as you can see, the RF switch has a really valuable performance. Now the comparison comes here. We use another important and nice device from the Tektronix. It's a probe P7720, which goes up to 20 gigahertz. It has tri-mode input, which enables the single-ended or differential measurements with single connection. As you can see in the picture, we have the probe and we have the fixture, which allows you to connect the probe to the SMA. It's a kind of an adapter. Probe can quickly change from the high impedance to 50 ohm. The S parameters are embedded inside the head, and as soon as you connect it on the scope, it will be loaded on the scope and it will be de-embedded. And it supports HDMI version 2.1, DisplayPort version 1.4, MIPI and M5 standards. Now let's see the setup here. We just removed the switch and inserted the probe inside the setup to make a comparison between two different options. One was the RF switch, which I already mentioned, and the other one is the probe. Let's look at the probe results. So in case of probe, we have the eye height of approximately 800 millivolt in the best case, and in the worst case we have eye height of 294 millivolts approximately. And the table shows that all the CTS results have passed the test. And as we mentioned, we only used one lane here just to show you the concept. And you see that we tested the results at TP3 EQ point. Let's now compare the previously shown setups. On top you see the S46T switch matrix eye diagrams for best case and worst case, and below you see the probe 7720 results. As you can see, there is only 4% difference between two instruments. 4% is not much. So we have a bit of signal degradation when you use the S46 switch matrix. So the customer has two options. Either he can sacrifice 4%, but at the same time he saves costs, he saves time, and he has no intervention during the measurement because the switch matrix allows the customer to automate his measurements. However, if he uses the probe, he can have 4% better signal quality or performance, but he needs to intervene during the measurement and swap the lanes as he is prompted. Here is a comparison chart. On the vertical axis, you see the millivolt or I height, and on the horizontal axis, you see the technique. We have shown the reference, and we have shown two different setups. As you can see, there is a subtle difference between the switch and the probe. So what to do if we have a limited budget? As you can see on the right side, we introduced the Keithley Tektronix switch setup, which is more inexpensive solution, almost the same performance as the probe, and most importantly, easy automation of the measurements with the switch. On the right side, you see if you want to do your CDS measurement, you need 4 probes, 4 adapters. This leads to a higher price, also gives you the highest performance with a wide range of applications. So there is a cost trade-off. If the customer has higher budget, he goes for the solution which is depicted on the right side. But if he has the lower budget and he wants to do his measurement in an efficient and automated way with a bit of performance degradation, he uses the Keithley RF switch matrix. Don't hesitate to contact us. We will consult you in the best way. Thank you very much. Contact us in case of any questions or any needs. We consult you in the best way.
So let's start with the demonstration. What we have here is the RF switch, real-time scope 33 GHz, front panel of the real-time scope. We have the AWG to generate differential signal. We have the probe here, as you can see. This is the second setup with the adapter. So the probe has 3 modes. You can, using this knob, switch between 3 modes. And you can adapt it to the SMA, which later will be used to connect to the AWG. What I generate here is the differential signal HBR3 8.1 gigabits per second. I'm using Tektronix AWG to emulate the signal generation. So here is the probe P7720 in my hand, as you can see. So it's a very nice probe with nice features. We call it tri-mode probe. There is a knob here. You switch between different modes, differential mode, single mode, as you can see here. And it's a nice tool to do your troubleshooting when you have your circuit. So you have different probe tips. As you can see, there is no tip here. For our application today, I have an SMA adapter. This is the SMA adapter kind of tip, which I will connect it to the AWG. You easily connect this adapter through this clamp here, and you slide it in, that's all. And as soon as you connect the probe to the scope, you see a green LED here, which means the probe is operating. And another nice feature here is that the all S parameters are de-embedded here. When it is connected to the real-time scope, the S parameters are loaded into the real-time scope and will be automatically de-embedded, and the correction will be done. So you don't need to be worried about the frequency corrections. That will be done automatically. We see 2 differential signals here, channel 1 and channel 3. We generated it 8.1 gigabits per second to emulate HBR3 DisplayPort 1.4 as standard. So in order to open the DisplayPort software, you should go under the Analyze. So when we go into the Analyze menu, we have variety of softwares for measurements and tests and estimation and calculation, which is amazing. For us, important today is the DisplayPort software. So we look under the menu for Take Express DisplayPort, which is here. You click and you open the software, and the GUI pops up. So under the Setup menu, we have different submenus. As you can see, we have Data under the test, Test selection, acquisition, and preferences, which I'll be going through each of them. On the first Data under the test, it's very important for you. You should select here your measurement combinations, as I mentioned earlier. What we have here, we have our det ID. You can rename your measurement test. We have two options. You can either acquire your waveform live, or you can use a pre-recorded waveform. So it gives you this flexibility to use the live waveform or already saved waveform in your system. There is a view mode. So in the view mode, if you are doing a compliance test, you select the compliance test. But if you are doing the advanced mode, you just select here. Under view, you see advanced mode. So when you click on advanced mode, you have a possibility to change between the parameters which you want. You shouldn't just abide by the standard rules. But on compliance, when you are doing a compliance test DisplayPort, just click it on compliance. You have the option to change the version, CTS 1.4 or CTS 1.2. Today we are doing CTS 1.4, so it's already on 1.4. On the connector type, you can have a type C USB DisplayPort or a standard, which we are emulating today. So very important is the device profile. So under the device profile, we have all different measurement combinations. Data rates is reduced bit data rate, high bit data rate 2 and 3. So we are doing today HBR, high bit rate 3. So we click the other out, we uncheck them. Then come next to the pre-emphasis level, which we change the level to different dB values to see how good our signal is, how quality of the signal. So I'm going to just show one combination, which is 0 dB. And the voltage swing depends which voltage swing you want to use. Now today we are going to use 800 millivolt peak-to-peak differential voltage. So that's why I unchecked this option 0 and option 1, which are 400 millivolt and 600 millivolt. So the standard defines that you have two options. If your data under the test supports a spectrum clock, you have to enable here. If you don't want to use it, you disable, or you can test and do your measurements for both. So let's now disable this because we are just emulating the differential signal using AWG. So I put it on disable. There is a dot automation mode, which gives you another feature. You use it manually or you use another DisplayPort fixture, which is called DPR 100, which will not be showing the DPR 100 today. So you set it on manual. Under the lane setup, you select how many lanes you are going to test. Now we have one lane. So you see here, one lane. You select the one lane, and this is the lane 0. And you select your channels, and these channels are the channels which are connected to your real-time scope. So you should be careful how to select the channels correctly. So in our setup, we have channel 1 on and channel 3 on. So I select lane 0 for channel 1 positive source and channel 3 negative source. And I click OK. So we test just one lane. And now comes the most important thing into the play. So when you click the setup here, you go to the RF switch matrix setup. Very interesting and very flexible GUI, you see. Under the switch setup, you select your configuration. This RF switch which we have here is Kittley S46T. So I select the RF switch. Under the link width, you have the possibility to change between the number of links. So we have 4 links. I select 4 links. Another very interesting feature, you can use this GUI to de-embed your signals. If you have your de-embedding S parameters, you use the de-embed here. As you can see, you can de-embed for all relays and switch. You can de-embed them separately, and you can de-embed even each connections. You select whatever you want here, depending on your measurement instrument, depending on your test setup. You initialize your switch with an appropriate GPIB address here, and you can apply also the embedding settings here. So the GUI, as you can see, we have here 3 to 5 relays. Now I turned on relay A and relay B, and I put the signal through first output of relay 1 and first output of relay 2 to emulate my 2 lanes. So you close the GUI. You have the possibility to save your configuration for later use. I'm not going to do that. And you come to the main GUI. And you have the signal validation here. Since we are emulating, I'm going to validate my pattern, but I'm going to move away for the validation because we are using PRBS 7 right now, which is not a pattern for HBR3. And there are other different menus, which I explained it in my webinar. For the sake of brevity, I can show you simply the test selections you can have. So what we can select here, different test selections, combinations, I diagram, pre-emphasis, non-pre-emphasis, and jitter analysis, because we have a very nice software DPOJet, which is combined with this software to do all the jitter decompositions and analysis, which is a main factor, one of the main factors of DisplayPort measurements. And in the status, when you run the measurement, it shows at which state it is, and you see how you will run and how good the measurement is going. And under the report, another nice feature, which you see you can save all the waveforms, all the data in different formats in HTML, MHT, and in PDF formats. So after you selected your correct configuration with the switch matrix, you just start here, and the measurement will be done automatically without any intervention. That's the nice feature of RF switch, which in combination with the DisplayPort software you can use to save time and to do it in an efficient way. Otherwise, you had to switch between the lanes for testing because the DisplayPort measurement tells you that you need to test the separate lanes. But this switch in combination with the software allows you to save time and do it automatically. So when you press run, the software does all these measurements and combination. I can show you the results. So here are the results, as you can see. At the end, when the software ready is, it gives you all these measurements and evaluations. You see now 2 eye diagrams, one for the best case, which we assume that there is no cable in the DisplayPort measurement, and one is the worst case. And you can see the mask here in both eye diagrams. All these measurements will be saved and shown for you. And the tables, which you can see, the measurements tables for different lanes, different measurements, and the test results will be pass or fail here if you have a problem in your test setup. I hope you found this webinar beneficial. Thank you for watching us. What we learned today is the DisplayPort software, and I showed you 2 different options. I showed you the RF switch, I showed you the probe, and we compared the results, which gave rise to the same results. I showed the software of SDLA, how to do easily the embedding. All of this allows you to save time and to do the measurement in an efficient way for DisplayPort measurement. Please visit our website and ask for a free trial. Thank you very much again.